Okay, last time we come to the topic of AC network, right? And then we talk about the sinusoid. Sinusoidal waveform, right? That's when we talk about the AC signal. The signal mostly is come in the term of sine or cosine, right? In cosine, omega t plus some phase shift, right? And then for the voltage, that represent in the term of V max cos omega t plus theta v. We can represent this voltage in term of phasor, which is the RMS value is V max divided by square root 2 and with the angle of delta V, right? Here. Yes, delta V here. Okay. Also for current, IS, this is I max cos omega t plus theta I. So I in the term of phasor is I max divided by square root 2 and theta I. For example, this if I is in maybe delta I is negative, we can if it's negative, you can represent in this form, right? I max divided by square root 2. Okay. So with this representation of phasor representation is make us very much more convenient, right? Very much more convenient to show this type of signal, this type of source. Okay. Then we talk about the impedance, right? C is R plus Gx, that is the response of the inductance L to AC signal. We can represent this inductance into XL is equal to JXL is J omega L, right? Or is J and 2 pi FL. And for the capacitance, XC and JXC is 1 by J omega C, right? Or 1 by 2 pi FC. So if we have both R and L or R and C or RLC, we can represent this load as R plus Jx, right? Here, and this V is in the term of phasor, right? It's a vector and this is also the vector. And we saw the circuit in terms of complex form, right? Okay. So we don't need to use the signal representation, right? Sine or cosine. It's difficult to solve, right? And then we represent this voltage in terms of RMS value with the phase angle. Okay? And the phase angle will represent the phase shift of the signal here. And we solve the circuit in complex form for AC system. Okay, for AC system. So I take maybe some example. So for example, if we have the voltage and connect to the resistance and the inductance, maybe the resistance is 5 ohm and inductance 0.1 ohm, and we have the voltage of square root 2 to 20. Voltage is square root 2 to 20 cos 2 pi ft plus maybe 2 pi ft, maybe at the reference angle, right? And the frequency of the system is 50 Hz. Therefore, 220 cos 2 pi 50 t, like this, right? This is Vs. So the voltage is in the form of cosine with the peak of square root 220 volt. So to solve this circuit, we better represent it into the phasor form. So to represent this circuit in phasor form, phasor representation, we get this voltage in terms of phasor. This is R and L. L will be transformed into the reactance or XL. So R is 5 ohm and the reactance XL is JXL is J2 pi FL, right? And 0.1 is equal to J2 pi 50 into 0.1 here. And then for the voltage, it will be VIMS. So it's 220 with the angle of 0. So how much for X? Yeah, 2 pi 50. Pi F is and then 31.4, right? 31.42 G 41.42. Those the impedance is 5 plus J 31.42. So we can calculate the current in phasor form as well. The current will be V by impedance, right? As 220 divided by 5 plus J 31.42, like that. So we get the current. So we can see the current will be in like the voltage, right? It's a negative angle. There's some angle. This will be negative value, right, for the angle of the current. So in this case, the voltage will be like this. This is V, and this will be the current with a negative angle. So this current can be also represented in the waveform, right? This current. This will be IRMS into square root 2 and cos omega t plus theta I. Yeah. So So with this method, we can calculate the sinusoid waveform by complex number, right? Just transform everything into the RMS value and the inductance and capacitance will represent into the reactance value or XL. Okay, then we talk about the complex power. So when we calculate the power of the AC system, for the AC system, the power for DC system we just the power equal to V into I, right? V into I, and we have only the real power in the term of watt. But for AC system, we call the product of V and I. We call complex power, or S is V is the in phasor form into I in phasor form with the conjugate of I. So we put conjugate here to represent the direction of the reactive power. Okay, and this is it. We call S as a complex power, or sometimes we can call it apparent power. The power that appear by voltage and current, right? And then when we multiply voltage and current with its angle, right? The product of V into I will be the magnitude of voltage and the magnitude of current, and then the phase shift between voltage and current, right? Because the I is conjugated, the angle has become negative, right? Okay, we get this value. Okay. And then this value will include both real and reactive value. So the real value we call real power, and the reactive, the imaginary part we call reactive power. This is real and reactive. Okay. What mean by reactive? It means that the power that flow in the system, but we didn't use this. Okay. For example, the power of the inductance. In fact, the inductance just store the power and return it back, right? Charge and discharge, charge and discharge. This storage device. The power flow is there, but we don't use it. Okay, the power exactly dissipate to need, for example, is by the resistance only. Only the resistance that consume the power. Okay, but for other device like inductance and capacitance, it's just store and return to the system, right? The flow is there, okay, but we don't use it. So we call this part as reactive power. Okay, so in AC system we have two parts of power, real and reactive power. Okay, and if we divide the real power by the total apparent power, we call this index as power factor. And then this is real part, and the power factor is the power, the real power divided by total apparent power. Okay, the magnitude of the apparent power. Or we can represent this power in triangle form. Okay, P will be real axis and reactive power in the imaginary axis. Okay, imaginary power. Okay, maybe you can recall your knowledge about complex number, right? So just a complex number. Okay, and this is the apparent power is S with the angle theta. Okay, so cos theta is cos theta What is cos here? Is P divided by S, right? P divided by S, or cos theta would be the power factor. Okay, it's the same value. So power factor is the cosine of this angle. Okay, cos theta. Yeah. So P will be S cos theta, or S is V into I. Or we can also use Pythagoras, right? P square plus Q square is S square. Okay. P square plus Q square will be S square, right? Will be S square. This is just Pythagoras triangle, right? Therefore, the power factor will not greater than 1, because P cannot greater than S, right? P always less than or equal to S, so that's why the power factor cannot be greater than 1, right? Okay, if you compute the power factor and you get more than 1, there's something wrong, right? Okay. Okay, this is another example, right? So we have the sinusoid voltage supplied to R and L circuit here, right? To compute the current T, right? The voltage is 14.14 sine omega. Theta omega is 377 radian per 6. So omega is 2 pi f, right? Here, maybe f equal to 50, we get this value, I think. Okay. R is 4 ohm. L is 8 millihenry here. Okay, so we can compute XL is 2 pi FL, so it will be 377 into 8 millihenry, right? Here, 8 millihenry, right? How much we get for this value? Maybe 3, right? J omega L here. 2 pi FL. Okay, it's about 3 ohm here. So we have the impedance Z is 4 plus J3 here. Okay. So we don't use I for square root minus 1, right? When we talk about complex value, but in the circuit we use J instead of I, right? To represent the imaginary part, mostly we use I, because we avoid using, mostly we use J, we avoid using I, right? Because we use I for current. Okay, I for current. Then the voltage here is in the sine function, or we can represent Vt in the term of cosine, right? 3773, maybe minus 90 degree, right? Equal, right? It's equal to 14.14 sine T77T, right? So the voltage in terms of cosine is V equal to 14.14 divided by square root 2, right? Vrms, right? Vrms is Vmax divided by root 2. The angle of minus 90 degree. So we get this. And we have the total impedance is here, right? Then we can calculate the current in terms of phasor. The current would be V by C. So it's equal to, so this is 10 with the angle of minus 90 degree. It's 10 minus 90 degree divided by the impedance, right? This is maybe in radian, right? So yeah. So in the example, the calculation is in radian, right? Yeah. Now we divided voltage by 4 plus J3, right? So we can get this current. Okay, this current here. In terms of radian, we get 2 with the angle of minus 2.25 to 2.215. Yeah. Minus, the angle is negative. Yeah. Then the voltage is here, right? V, and the current is 2.215. What is 2.215? How much for the degree? 2.215 radian. So this one is 2 minus 1 to 6.9 degree. Yeah. It's about this. This is the current. The voltage is minus 90 degree and the current is minus 1 to 6.9 degree. Okay. And the power, if we calculate power, S will be V into I conjugate. We can just multiply the voltage here. It's 10 minus 90 degree into I will be 2 minus 1 to 6.9 with the conjugate, right? So this value we can get P and Q, right? We can get S in the term of P and Q. Okay. This is just represent the power in terms of sinusoid function, multiply sinusoid function together. Okay, you get the power in this term of sinusoid function. But in power calculation, we usually represent the power in terms of P and Q with the real power and reactive power. Okay, this example is for complex power calculation. Okay, to find P S equal to P plus JQ if the voltage is this value and the current is this value. Okay, the voltage will be represented in terms of phasor, right? And the current also in terms of phasor. Okay, you can also write in terms of degree, right? This is the radian. I think this in radian. This is also in radian, right? And if we represent in terms of angle, what is the degree of this angle? 0.262. 0.262. It's 15, right? This is V is 100 divided by square root 2 and 15 degree, and for I is 2 by square root 2 and same, right? Just negative value 15 degree here. You can write in this term as well. Instead of radian, we can use degree, right? Degree term, maybe more familiar with you. So the complex value is we just Vs is Vi conjugate, right? Vi conjugate. Then we get 100 by root 2 into 2 by root 2 with 15 plus 15, right? It's 30 degree, right? You get 30 degree, yeah. And then it's equal to 2 is 100 with 30 degree. This means S, what is S? If we, in terms of P and Q axis, S will be, we have, this is 30 degree, this is 100, right? So we can calculate how much P and how much Q, right? How much reactive power. This will be 100 with cos 30 degree plus J sine 30 degree is equal to 86.6 plus J 50. This means the real power is 86.6 and the reactive power is 50, right? And the unit of this is VA, and this is what? Unit of reactive power is VAR. We call VAR, VA reactive here. So what is the power factor of this power? What is the power factor? The question is, what is the power factor? PF. What is the power factor of this example? So anyone can tell me what is the power factor of this example? The power factor is P divided by S. Therefore, the power factor is 0.866, right? So the power factor is 0.866. Okay. And then now we talk about the three-phase power. So what is three-phase power? Due to when we transmit the large amount of power of electricity, the large amount of power of electricity we at this moment, the technology we transfer the electricity is we transfer in three-phase form, three-phase power. So we don't transmit the power only one single phase, but we transmit the power in three-phase because of the economic reason. Okay? For long distance, so we use three-phase system for large power generation and transmission to the town. Okay, and for three-phase power, we will have the voltage with three-phase shift. Okay, we have phase A, phase B, phase C, and the angle is shift to each other by 120 degree. Yeah. For 120 degree. And for the large power generation, we use the generator. The generator will generate. The generator will generate three-phase power: phase A, phase B, phase C, and each phase will have the voltage, the same magnitude of voltage, but the phase shift by 120 degree. And then when we draw the phasor, usually we use phase A as reference. The reference angle is 0, right? And phase B is equal to VA with the phase shift lag VA by negative 120, okay, minus 120. And then phase C will lag up to the next 120. So VCN will be VAN with minus 240 degree here. Okay. It means that VCN will lead VAN by 120 degree. Okay. Yeah. And we have the voltage between the line and neutral. We call VAN, right? VAN, VBN, VCN. And the voltage between line and line, we call line to line voltage here, or VAN, or VAB, sorry. VAB will equal to the magnitude of phase voltage, or VAN, is square root 3 of VAN. Okay, it's root 3 times of this voltage. Okay, here on VAN is here. Is the voltage. If we find these two vectors plus together, right? This VAN and VBN. So VAB will be root 3 of VBN with a phase shift of 30 degree. This is 30 degree. This phasor and VAN. We have the angle of 30 degrees. So it's square root 3 of VAN with another 30 degree phase shift here. Okay, we get this value. So when we can talk about three-phase power, we will have V line to neutral. It means VAN or VBN or VCN, and V line to line, or VAB between line to line, VBC or VCA like this, and V line to line will equal to square root 3 of V line to neutral. Okay. So for example, the voltage of the power distribution in this campus. Okay, in this campus, we transmit the three-phase power. You receive this type of electrical pole, right? Nearby the roadside, right? So this is three-phase power, and we transmit the power of 22 kV. This means this is V line to line, 22 kV. Okay, and for this building, we will have from the transformer into this building, we will have the power of about 400 volts. This means line to line. Okay, and we have neutral, the line to neutral. V line to neutral is 400 divided by square root 3 here. Okay, so in the large factory or in large building, we will have the power of three phase A, B, C, and we also have the neutral line. Okay, and line to line, the voltage reference is 400, or we use 380 volt as reference, and 380 volt, and this is also in between line to line is 380 volt. Okay, so we routing the electricity with three phase. Okay, but when come to this room, we have only line and neutral, right? For example, this room may use line and neutral. The line and neutral voltage would be 380 divided by square root 3 is equal to 220 volt. So this is 220 volt. Come to this room. Okay. Come to another room, we have maybe V and N to another room. Okay. So it's different of the load. Okay. A, B, C, and N. A and N. Okay, two, one load. This is single phase. Here, another single phase. Here, another single phase, right? So the voltage supply in three phase form. Where we can use single phase, or we can use three phase as well. Okay. For some type of load, we will use three phase. Okay. Maybe large machine can use three phase. Okay. And for lighting, or maybe just small load, right? We use single phase. Okay. So for the power generation, transmission, distribution into the large industrial load, usually is in the form of AC three phase. AC three phase system. Okay, when you work in the large factory, the power supply to the machine will be usually in three phase power AC. Okay. Here. So the representation is VA, VB, VC with the phase shift of 120. VA is the blue line, right? And for VB is shift for 120 degree, and VC is another 120 degree. Okay, this is the signal, right? But we represent this signal in phasor form. Okay, we have VAN, VBN, VCN, and then we can calculate VAB, VBC, VCA as well. Okay. And VAB or V line to line is V line to neutral into square root C. Okay. V line to neutral is V line to line divided by root 3. Okay, and if the system is balanced, it means we use the same power from three phase. Phase A, phase B, phase C. If the system is balanced, the total apparent power can be calculated by square root 3V into I. And V is mean V line to line. This means the voltage between line is equal, right? This is also V line to line. This is V line to line. Okay. The magnitudes of V line to line of three phase are equal. Just the phase shift, right? It's different phase shift. We can calculate S by square root 3 into V into I. Okay. And three-phase power, real power is S cos theta. Okay, because S will be in terms of P plus JQ, and then this is P, this is S, and this is Q. Right? This is theta. So S cos theta will be the real power, right? P by S is cos theta. So P is S cos theta, or root 3 into V into I cos theta. Okay, I will show you maybe two examples, okay, and then we take it, right? Okay. So we have three phases of the load. Okay, this load is the motor. The voltage supplied to this load is 380 volt, and we measure the current at 50 amp, and the power, the real power is 285 kilowatt. Okay. So what is the apparent power? Okay. So with this voltage and current, we can calculate the apparent power by square root T into V and I. Okay. S is root 3 VI. So, but with this formula, we get only the magnitude. Okay. But we don't know how much P and how much Q. We know only the magnitude of S. We don't know the angle, right? We don't know the angle of S. So, because we know only the magnitude of voltage and the current, we know the absolute V and we know absolute I. We don't know how much the phase shift between V and I, right? Okay. So in this case, we get the apparent power at 329.09 kilo VA, right? kVA, kilo VA, yeah. And we know that the real power is 285. So now we have the information. If we have the meter to measure how much the watt of the motor, right? So total is 285, and this is 329.09. So now the information is enough to compute, right? So the power factor is 285 divided by 329. Yeah, it's 0.866. Yeah. So this power factor will equal to the cosine of this angle, right? Okay. Then we can also calculate this theta. The theta will be the inverse cosine of 0.866, right? Here we can see how much P, how much S, and then we can also calculate Q, right? Can we get the Q value, right? Can we get the reactive power of this motor? Now we can get the reactive power of this motor as well, right? By calculate from S and P. Okay. So we can calculate Q by square root S square minus P square, or Q maybe S into sine theta after we get theta, right? Or we can get Q by P into tan theta as well. Q by P is tan theta, right? Q by P is tan theta. Okay, let's see another example. Compute the apparent power, reactive power, apparent power, reactive power, and power factor of three-phase AC system. With we have the terminal voltage 380 volt, the current is 100 amp, the real power is 4 kilowatt. This is the real power, and this is voltage, and this is the current, right? And usually when you measure the voltage and current, for example in the laboratory, if you voltmeter, you get only the magnitude value, you don't know the phase angle. Okay, similar to the current, when we measure the current value, we know only the magnitude, we don't know the phase angle, right? And we can measure the power, right, in terms of watt. This is the information that we can measure usually in the factory, okay, or in the AC system. But the phase shift is there, right? The phase shift is there between these three values. So in this case, we can compute S, right? Absolute S is equal to absolute V and absolute I. Square root 3, sorry. Because this is three phase. For three phase system, don't forget square root 3, right? So it's root 3, 380 and 100 we get. This is absolute S, so this is 658.18, right? And P is 400 kilowatt. This is kVA. So right now we can calculate Q, right? And also we can calculate this theta value. The power factor is 400 divided by 658.18. This is a power factor. Or we can calculate the theta is cos inverse of 0.608 here. Okay. We can have power factor, we can have relative power value, okay, of this system. Okay. Maybe the ratio is quite complex, but finally when we compute the system by phasor, okay, it's not very difficult, right? Just to make understanding of how to use the relation between each parameter, between each variable. If we know the relation of each variable, right, for AC system, we can calculate for another the remaining variable that we don't know. Okay. Okay, this is the homework for you, right? Just do. Any other? Okay, and this is the homework for you. So if we know the power factor, what happened? If we know this is if we know S, absolute V, absolute I, and what we know power factor, what is absolute S by P, right? So if we know power factor and we know S, we can calculate P as well, right? And then V is going to calculate Q, right? Okay. So time to do this homework also. Okay, any question? So we take some small break, right? Okay, for maybe 5 minutes.